Okay, so hello everyone. Welcome to the live problem solving session for week 12 of the course Computational Competitive Algebra. So this is instructed by Professor Manoj Kummini, and this is the final live problem solving session of this course. And we are at the end of this course. So let's summarize the topics of week 12. After that, I will start solving some problems based on these topics. So in week 12, uh, we started with by defining what is known as monomial submodules. So this is an analog concept of monomial ideals. So basically, monomial submodules of a free module of finite rank. So in that case, we have defined monomial submodules, and we have seen analog concept of monomial order and Grosvenor basis and Buchberger's theorem and those things. So analog of Buchberger's criterion in case of monomial submodules. And after that, our goal is to prove that the Hilbert-Szijigi theorem. So proof of Hilbert's Szijigi theorem. So we proved it for monomial ideals, and we uh, basically we have reduced to the case of monomial ideals, and we have proved it for monomial ideals, and we have indicated that how we can reduce it to monomial ideals. And basically, for the one part of Hilbert-Szijigi theorem, we need causal complexes. So for those things, we need some homological definitions from homological algebra. So again, we came back to complexes, or basically these are chain complexes. So we have defined complexes and homology of complexes, and also homomorphism of complexes or map of complexes, map of complexes. Then from a map of complex, we can also do the short exact sequence of complex, and after that we have seen basically the horseshoe lemma. So short exact sequence of complexes. And yes, from a short exact sequence of complex, we can induce a long exact sequence of homologies. So induced long exact sequence of homologies. So in the lectures, we have seen this long exact sequence only for the our purpose only in the case of causal homologies, but it is true in general. So that can be proved using Snake's lemma, but that's okay. So it's induced long exact sequence of homologies, and after that, if we have a map between two chain complexes, then we have seen how to define one more complex, basically the mapping cone. Mapping cone of a map of complexes, and in this case we have a special type of short exact sequence of complexes which involves this mapping cone, and from that we also get the long exact sequence of homologies. That part we have already seen. So mapping cone of a map of complexes. Then using this mapping cone, we have defined a causal complex of a sequence of elements. Of a sequence of elements in the ring. So we have defined it inductively using mapping cone. And we have also saw some properties. So some properties of this causal complex. So basically, one important property that how regular sequences and causal complexes are related, or when a sequence is regular sequence, that can be determined using causal complexes. For that, first we have defined what do we mean by regular sequences. Then when causal complex gives when a sequence is regular sequence. So when a sequence is a regular sequence using causal complex, and yes, and the more general part is when causal complex gives a minimal free resolution. uh, yes, when causal complex of a sequence, let's say x1 up to xn, gives minimal free resolution, of the quotient ring R mod x1 up to ideal generated by x1 up to xn. So using that part, we have concluded our proof of Hilbert-Szijigi theorem when the ideal is a monomial prime ideal. Because a monomial prime ideal is basically an ideal which is generated by the variables, and variables in the polynomial ring forms a regular sequence. And after that, we have defined projective dimension. Uh, projective dimension. Also the Castelnuovo-Mumford regularity. Castelnuovo-Mumford regularity or just regularity. And applications of this regularity in Hilbert functions, that when the uh, Hilbert function coincides with the Hilbert polynomial, so that part can be determined using regularity. So applications of regularity to determine when Hilbert function coincides with the Hilbert polynomial. Hilbert function coincides with the Hilbert polynomial. So, suppose we have this Hilbert function and we have this Hilbert polynomial. Suppose this is true for all n greater or t greater equals to n. So that stage n, so that least possible number n. So that is actually known as the postulation number. So from regularity we can give an upper bound for this postulation number. So basically this should hold for regularity of m plus 1. So this postulation number should be less equals to regularity of m plus 1. So this is an important application of the regularity. And also we have saw some geometric applications of this, how to transform things in case of regularity and Hilbert functions. Okay. So this is the rough summary of the topics of week 12. So there are lots of topics actually, but I hope it's fine. Okay, so maybe now we can start solving some problems. So the first problem is, so let okay, let alpha dot from f dot to g dot be a map of complexes. So that means this f dot and g dot are two complexes, and this alpha is a map between f dot and g dot. Then show that alpha dot is an isomorphism. Okay, so show that if alpha dot is an isomorphism, then the map induced at the homology level, then the map at the homology level so the induced map at the homology level is denoted by this, is also an isomorphism. So if alpha dot is an isomorphism, then h dot alpha dot is also an isomorphism, and also give some example to show that so that the converse need not be true. Okay, so what is the question here? So f dot and g dot are two complexes, and alpha is a map between them. Then this alpha will induce morphisms at the homology level. So homology level of f to homology level of g, we will have map which will be denoted by h of alpha. So then this map at the homology level will be an isomorphism if alpha itself is an isomorphism. But if h dot alpha is an isomorphism, then alpha need not be an isomorphism. So converse need not be true. So we have to prove that part. So okay, first, I should recall the terminologies so quickly. So let's recall the definitions. So first, I will recall complex, map between complex. So a complex, so the first definition is complex, so that I don't need to recall it again and again. So a complex, let's say F, uh, F is a sequence of uh, R module homomorphisms So how to write it? So our complex is basically denoted by f dot, and it is, this is the n plus 1th module of the complex, this is the nth module, this is the n minus 1th module, and this will so on. It will go like this. This is the n plus 1th map, this is the nth map. So it is a sequence, basically it's a sequence of R module homomorphisms such that if n compose if n plus 1 is equals to 0 for all n belongs to Z. So what this is means, so if we take the composition at each stage, so here we can take fn, compose fn and fn plus 1, so then this would be the zero map. So what does it mean? It means image of fn plus 1 should be subset of kernel of fn for all n belongs to Z. Then we call it a complex. Basically it's a chain complex because these indexes are in the decreasing order. If it is in increasing order, then we call it a cochain complex. Now what do we mean by homology? uh, so note that at every fn, this image of this previous map is kernel of this next map, right? So image of fn plus 1 is subset of kernel of fn. So we can consider this quotient kernel of fn modulo image of fn plus 1. So this will be the homology at the nth stage. So so homology of a complex, again I will denote it by f, is denoted by h dot f dot. This is also a complex, is a complex denoted by, okay, need not, so it is just a module, not need not be a complex, is denoted by this, where the nth homology module of f dot is equals to just the kernel of fn modulo image of the previous map. This is true for all n belongs to Z. Okay, so this is the definition of homology and map of complex. So suppose you have f dot here, which is fn plus 1 dot fn to fn minus 1 to dot dot so on, and you have another complex dot dot gn plus 1 to gn to gn minus 1 dot dot so on. So here you have fn plus 1, here you have fn, here you have gn plus 1, here you have gn. So this is one complex, this is another complex. Now a map between these complex means map at each module. So let's denote it by alpha dot. So a map is alpha dot. So it will be a map at each level. It's a sequence of maps such that each square should be commutative. So that is the definition of map of complexes. Now if you have a map of complex, then alpha dot uh, kernel of, let's say, fn plus 1 will be subset of kernel of gn plus 1. Sorry, let's say n, let's take n, and al okay, let's say alpha n, and alpha n of image fn plus 1, this will also be subset of image of gn plus 1 for all n belongs to z. So this we have seen that a map of complex will take kernel to kernel and image to image. So from this we can conclude this alpha will induce a map on the level of homology. So it will be hn of alpha dot from hn of f dot to hn of g dot. And how it is defined? That hn of alpha dot, if you take an element from the homology, let's say x plus kernel of fn, then it will be just alpha n of x plus kernel of gn. And this is true for all n belongs to J. So we need to prove that if we are given this map alpha, if is alpha is isomorphism, then this hn alpha is also isomorphism, but the converse is not true. So how to prove this? Now come back to our problem. Now come back to our problem and let alpha is an isomorphism. Okay. So we need to prove that we want to show hn alpha dot is an isomorphism uh, for every n belongs to Z. So let's do it for a fixed n. So first we will prove the injectiveness. So let hn alpha dot of x plus kernel of fn is equals to 0 plus kernel of Gn. So what we are doing? So okay, I should write one more step. So let x plus kernel of Fn belongs to kernel of Hn of alpha dot, right? So we are taking an element from the kernel of this map. So we need to prove that this element is 0 so that this map becomes injective. So it is in the kernel means image of this map is 0. And what is the image? It is alpha n of x plus kernel of Gn. This is kernel of Gn. So that means alpha n of x belongs to kernel of Gn. So that implies Gn alpha n of x is equals to 0. So we need to go back to the diagram. So Gn compose alpha n is 0 means this part. So x belongs to here. Our x is here. So x is here and x maps to here is 0. So from this side also it will be 0. So it is alpha n minus 1 compose Fn. So this implies alpha n minus 1 Fn of x equals to 0. This is by commutativity of the square. That implies so what we are doing here, that this Fnx belongs to kernel of alpha n minus 1. Uh, so Fn kernel of Gn. Okay, so what we want to prove? Uh, so we are taking kernel here, kernel of Fn here, x plus kernel of Fn maps here, which is alpha n of x plus kernel of Gn. Alpha n minus 1 compose Fn. So Gn compose alpha n is 0. Okay, so x plus Fn belongs to kernel of this. Okay, but our alpha, so this will imply fn x equals to 0 because this kernel is 0. So because alpha n minus 1 is 1 1. Now fn x is 0. So this will imply x belongs to kernel of fn. This will imply x plus kernel of fn is 0 plus kernel of fn. So this element is 0. So this means kernel of hn of alpha dot is basically 0. So this will imply hn alpha dot is 1 1. So we have to use the injectivity of the original map alpha, right? Then we are proving that alpha, the map at the homology level is also injective. Now the surjectivity. So surjectivity is easy. So we need to prove that hn alpha dot is surjective. So we want to show hn alpha dot is onto. So we need to take an element from the image. So let y plus. So okay, my image. So yeah, this is little bit wrong. So this should be x plus image fn plus 1. Yeah, I have written wrong here also. Oh, yeah, so this is image fn plus 1. This is also image gn plus 1. So then it is an element of the kernel of gn modulo image of gn plus 1 at the nth homology. Yeah, so I need to modify it here also. No problem. Wait. So it is image of fn plus 1. It is image of gn plus 1. So alpha n of x, it is image of gn plus 1. It is also image of gn plus 1. So alpha nx is in the image of gn plus 1. Okay. So alpha nx is equals to gn plus 1 of y. So where is gn plus 1? Yeah. So y belongs to gn plus 1. So gn compose alpha n then will be 0. So this will imply gn compose alpha nx is equals to gn plus 1 y will be 0. Now gn compose alpha n, what is this? Yes, alpha n minus 1 compose fn. Yeah, so we have to add just one more line, then we are done. Maybe I will add it here. Yeah, it's fine. Oh, So from this we will say alpha n minus 1 fn of x is 0. So fn x is the kernel. So alpha n compose gn, sorry, gn compose alpha n. Yes, gn compose alpha n is 0. So alpha n minus 1 compose commutativity of this square. Gn compose alpha n is same as alpha n minus 1 compose fn. So fn x is in the kernel of alpha n minus 1. So which is same as so we need to use the other part, exactness, which is same as the so this is same as image of uh, alpha n, right? So this will imply, so this will imply fn x is same as some alpha n of z, where z belongs to fn. Yeah, that okay, image of alpha n. Yeah, so what we want to prove that x plus image fn. Oh, oh, so x belongs image fn is 0. So we want to prove alpha nx plus uh, x plus image fn is 0. X belongs to image fn. Okay, so here this is itself 0. Oh, oh, sorry. This is 0. We are right because alpha n minus 1 is 1, 1. So this will imply fn x is 0. So x belongs to kernel fn, which is same as image fn minus 1. Sorry, image. So x belongs to kernel fn, which is same as image of fn plus 1. So this will imply x plus image fn plus 1 is same as 0 plus image fn plus 1. So that is what we wanted to prove. Yes, this is n plus 1. So we are taking this element from the kernel and we want to show this is 0. So that is what we have done. So kernel is 0. So this is little bit I have made little bit mess, but it is understandable. Okay, now prove the surjectivity. So let y plus image of gn plus 1 belongs to nth homology of g. So this implies y belongs to kernel of the nth map. This is subset of gn. Now there exists x belongs to fn such that uh, alpha n of x is equals to y because alpha n is onto, right? Now uh, uh, we need to prove that alpha nx we want to show alpha. So yeah, we want to show x belongs to kernel of Fn. So now gn of y equals to 0. That implies gn of alpha n of x equals to 0. So let's look at the diagram. Gn of alpha n is 0. So alpha n minus 1 Fn is 0. So this means alpha n minus 1 Fn x is 0. So this is by commutativity. But alpha n is injective. So Fn x is 0. Since alpha n minus 1 is 1 1. And this imply x belongs to kernel of Fn. So uh, what we are getting that if we take alpha n, sorry, h, so we are taking hn of alpha, the map at the nth homology, hn of alpha, and evaluate it at x plus image fn plus 1. So then it is basically alpha n of x plus image of gn plus 1, and alpha n of x is y. So this is y plus image of gn plus 1. So it is surjective. So this is just diagram chasing, uh, nothing wrong, nothing complicated. So Hn is isomorphism. This completes the proof. So alpha is iso will imply H of alpha is also iso, but this converse need not be true. Let's see an example. But the converse need not be true. So for example, okay, let's take f to be the complex 0 to z to z to 0. Here this map is multiplication by 2. So this is one complex because here everything is going to 0. So 2z, uh, image of this map is 2z, which is subset of z, which is the kernel. So it is satisfying the condition for complex here, and also it will satisfy condition for complex here. And let's take the other complex as here we will take z mod 2z. Here we will take 0, and here it is also 0. And let's take this map, the natural map from z to z mod 2z, and here just take the everything is going to 0. So the 0 map. Then this is a chain map. So this is I am defining as our alpha dot. So clearly, so here alpha dot is not an isomorphism, because so let's take it is the 0th position, it is the first position, it is the second position, because alpha 1 from z to z mod to z is not injective, because it is the canonical surjection. And if we take alpha 2 from z to 0, so it is not injective. So it is not an isomorphism at both. So this map and this map both are not isomorphism. So this chain map cannot be isomorphism. But what are the maps at the homology level? So first we need to find the homologies. But now, so what is H? H0 is 0 because we have 0 here. So let's take H1. So H1 of alpha dot means homology at this. So kernel of this map modulo image of this map. So kernel is Z and image is 2Z. So this is Z mod 2Z. And what about H2 of alpha? Sorry, this is F. Sorry for my wrong notations. So homology at the second position means here. So kernel of this map. So this map is injective. So kernel is 0. And image of this map. Image, this is the 0 map. So image is also 0. So this is 0. Now homology of, first homology of G dot. So this is the first position. Kernel of this map. So everything is going to 0. So kernel is the whole module. So kernel is Z mod 2Z. And image is 0. So homology is Z mod 2Z. And we have no other module in this complex, so other homologies are 0. So what about H1 alpha from uh, H1F to H1G? So this is basically from Z mod 2Z to Z mod 2Z. It is basically, if we use the definition, then it is then this is the map equal to the identity map. So at the homology level, it becomes the identity map. So it is an isomorphism. So at the homology level, it is an isomorphism, but the original map between complexes is not an isomorphism. So this is a counter example for the second part. So this completes the first problem. Okay, so let's do the next one. Yeah, the second one. So let okay, I will use the same notations. So let alpha dot from F dot to G dot be the map of complexes defined by uh, alpha n is 0 or all n belongs to Z. Then uh, write down the mapping cone C dot of alpha dot. So basically we are taking the zero map between complexes. Then we want to write down the mapping cone. Okay, so let's recall what we mean by mapping cone. Then we will come to the solution. So recall mapping cone. So for mapping cone, we first need a map between complexes. So here you have a complex f from fn plus 1 to fn to fn minus 1 to so on. And here you have another complex gn plus 1 gn to gn minus 1 to dot dot so on. So here let's take the map fn plus 1. Here let's take fn. Here gn plus 1. Here gn. Now we need a map between this complex f dot to g dot. So let's take it is alpha dot. That means we have map at each level. So it is alpha n plus 1. It is alpha n. It is alpha n minus 1. So that this each square is commutative. Now how this cone is defined. So the mapping cone of alpha dot is denoted as C dot of alpha dot. How it is defined? So it is defined as so you take the modules at the diagonals and take uh, modules at the diagonals like so here I am taking gn direct sum fn minus 1. Here I am taking gn minus 1 fn minus 2. Here you can take gn plus 1 fn and so on. So this is the modules of the complex of the mapping cone. So remember that this is the diagonal uh, at this diagonal, right? Fn minus 1. So this is Fn minus 1. Now here what will be the maps? So this diagonal, so we have map from this diagonal, right? So from this object we need a map to this object. So from Fn we have two maps. One is this one and other is this one. And from Gn we have only one map. So to Gn we have two maps. So what will be this map? So from to Gn we have two maps. So one is Gn plus 1, one is alpha n. So this is Gn plus 1 and this is alpha n, right? And to Fn, Fn minus 1, we have only one map, Fn. So we will write Fn here, but we will take one negative sign. So this is the map. Similarly here it will be Gn alpha n minus 1, 0 minus Fn minus 1. And this will continue. And you can check that this forms a complex because composition of this with this will be 0. So now use this. Now come back to our problem. Now come back to our problem. In our problem, our alpha n is 0 for all n belongs to Z. So, okay, let me use this notation. So this is delta n plus 1. This is delta n. So this will imply delta n is equal to gn 0, 0 minus fn minus 1. This is for all n. So this means the mapping cone is just direct sum of this g dot with g dot, this complex, and f dot shifted by -1 and the minus negative sign, right? So it is just direct sum. If we take the zero map, then its mapping cone is just the direct sum of these two, because the objects are gn direct sum fn minus 1, that you can see, and maps are also just direct sum maps, component wise. So here maps is gn comma, okay, not gn, I could take another. So n comma b n minus 1 will map to basically gn comma n comma minus f n minus 1 comma bn minus 1. So this tuple will go to this tuple. So this is the problem 2, second problem. Okay, so using this we have defined causal complexes, then we have seen regular sequences. Now let's see some problem on regular sequence. So problem number 3. So give an example of a regular sequence uh, to show that uh, permutation of a regular sequence need not be a regular sequence. Okay, so permutation of a regular sequence need not be a regular sequence. So we have to give a counter example for this one. So let's recall the definition of regular sequence first. So what do we mean by a regular sequence? So let R be a ring, and let's say x1 up to xn belongs to R. Then this x1, x2, xn is a R regular sequence if the first one is that you take the element xi. This xi is a non-zero divisor on this R module, means this is the quotient. This is for all 1 less equals to I less equals to n. So what does this mean? This means x1 is a non-zero divisor on R, x2 is a non-zero divisor on R mod x1, x3 is a non-zero divisor on R mod x1, x2, and so on. Okay, so this is the first condition. And the second one is, if you take the last quotient r mod x1 up to xn, this should not be 0. Okay, now then in this case x1 up to xn is a regular sequence. But if we change the order, like if we take x2 first and x1 second, xn, then this sequence need not be regular sequence. So for that, we have to give some counter example. Okay, now come back to our problem. So let R be the polynomial ring in three variables. So polynomial ring in three variables x, y and z over the field K. Then our first claim is, if we take x, then y times 1 minus x, then z times 1 minus x, then uh, this is a R regular sequence. And claim 2, so if we permute this, like if we take z times 1 minus x first and y times 1 minus x second and then x, then this is not a R regular sequence. So let's prove these two claims. So proof of claim 1. So we need to prove that this is a regular sequence. So we have to check these two conditions. First one, this non-zero divisor condition, and second one, that we go modulo by the ideal, then it should be non-zero. Second one will be fine, but we should check the first condition. So the first element of the sequence, which is x, this is clearly clearly x is a non-zero divisor on R. Why? Because R is a domain. R is an integral domain. So every non-zero element is a non-zero divisor. Now if we go modulo by x, now we need to check for the second element. So now y times 1 minus x is a non-zero divisor on R mod x. This is basically k of yz, right? Because y times 1 minus x bar, this is same as y minus yx bar, but x is in there, so this will be same as y bar. So y bar is a non-zero divisor on R mod x. Similarly, so second element is also non-zero divisor. Now the third element. Similarly, z times 1 minus x bar will be same as z bar in R mod x comma y, which is same as kz. So similarly, this one is a non-zero divisor on R mod x comma y times 1 minus x. Oh, sorry, this is x comma y times 1 minus x. But this is same as r mod x comma y, because x is there, so y minus yx will be absorbed. So all three elements are non-zero divisor, and also, so if we go modulo by these three elements, x comma y minus yx, z comma zx. So this is r modulo x comma y comma z, and this is k, which is non-zero. So x, y times 1 minus x, z times 1 minus x is a r regular sequence. So this proves the first claim. Now proof of claim 2. So what is claim 2? That if we permute this sequence, then it is not an irregular sequence. So what we will do, that if we so z times 1 minus x is definitely a non-zero divisor, because we are in an integral domain. But if we go modulo by this element, then y times 1 minus x need not be an irregular sequence, need not be a non-zero divisor. So here y times 1 minus x is a zero divisor on r mod z times 1 minus x, because here z bar not equals to 0 bar in r mod z times 1 minus x, because z is not there in this ideal, and z bar times y times 1 minus x, this is same as y times z times 1 minus x, this is 0, because this is this element in this ideal, so this is a zero divisor. So z times 1 minus x, y times 1 minus x, and x is not a irregular sequence. So if we permute a regular sequence, we may not get a regular sequence. But there are sufficient conditions in those cases. If we permute a regular sequence, we will get a regular sequence. Okay. So problem number 4. So find the projective dimension and regularity of R mod I in the following cases. So the first one is R equals to kx comma y and I equals to ideal generated by x square y cube. Second case is again r equals to kx comma y, I equals to ideal generated by x times y. Let's take an earlier example. Yes, so again r is same kx comma y, but the ideal is x square comma xy comma y cube. Combination, the sum of the first two ideals. So for these three cases, we need to find projective dimension and Castelnuovo-Mumford regularity for R mod I. So how to do this one? Okay, so first let's recall projective dimension and Castelnuovo-Mumford regularity in case of polynomial rings. So let R be this polynomial ring k x1 up to xn, and I be an ideal, be a graded ideal. Let's take, because we will define regularity also, be a graded or homogeneous ideal. Then the first is regularity. So let so we already know the graded Betti numbers. So those are uniques. So let uh, so here you have R mod I, here you have 0. So here you have a free module. So it will be always R, but let's take the general form. So R minus J, beta 0 comma J, again direct sum of, so this is varying over J, R minus J, beta 1 comma J, and so on. So let this be a minimal graded free resolution of R mod I, right? Then these numbers beta ij, these are unique. These graded Betti numbers, these are unique numbers. Then we define regularity of I, regularity of R mod I, as the maximum of the difference j minus I, such that this beta I comma j, so it is of, oh, so Betti number of what? Betti number of R mod I. Betti number of R mod I. So this beta ij of R mod I is non-zero. So this is the regularity. So it can be defined in a more general setup using other things like local cohomology. But for our computational purpose, in this polynomial ring, we can define it in terms of graded Betti number. So this is the definition of regularity and projective dimension. So projective dimension is the length of this. This is the zeroth pre-module. This is the first one. So this will continue. This is the minimum possible length of the minimal free resolution. So, so the projective dimension projective dimension of R mod I is the minimum possible length of the minimal free resolution is the length of the minimal free resolution. So we are already taking minimum here is the length. So length of the minimal free resolution. Free resolution of R mod I. So that is the projective dimension. Now in these three cases we need to find these two numbers. Of course, one can do this easily in Macaulay too, but let's do these examples by hand because in these cases it is easy to do. So let's do the first one. So basically we need to find the minimal graded free resolution for the regularity. That's all. And that we have already done in the earlier lectures. So uh, it will not be difficult to do it. Now came back to our problem. Now coming back. So first one. So all our rings are polynomial ring in two variables. So R is always kxy. So let's fix this. And the ideal in the first case is x square y cube. So this is a regular sequence. So again the causal complex will give you the minimal free resolution. Or you can also calculate it by hand also. But so now x square comma y cube is a R regular sequence. So the causal complex of x square comma y cube is the minimal graded free resolution of R mod I. So we need to find the causal complex. So what is the causal complex? So now the causal complex of R mod I is it is the mapping cone, right? So you take 0 to R to R to 0. So this is multiplication by x square, and x square has degree 2, so we need to shift it by 2. And again we need to take the same complex and let's take multiplication by y cube. So this is the map between complexes, and the mapping cone of this chain map is the causal complex. So the mapping cone of the above map of complexes is the causal complex of x square y cube. So let's find the mapping cone. So the first module is this diagonal, second module is this diagonal, third module is this diagonal. So let's write it down. So it is r. So first is this, means r direction 0. So it is r. Second is this one, r direction r minus 2. So r direction r minus 2. So now we need to take the map from here to here. So one map it is 0, but so it is 0 map. So the thing is this map and this map. So this is multiplication by x square. So this is just x square y cube. But this is multiplication by y cube. So we need to shift the degrees by 3. So it will be 3. So maybe we need to write in the other way because, yeah. So r minus 2, r minus 3. Now we need to take this diagonal. So this is r minus 2 to r minus 2 multiplication by 3 y cube of degree 3. So 3 more should be shifted here. So it will be r minus 5 to here from 0. And this is basically minus, so map is from this module to this module. So one is yq and we need to shift one sign minus x square. So x square yq. So this is the causal complex, or this is the pre-resolution. So this is the 0, this is the first slot, this is the second. So what will be the regularity? So this is the 0th position, this is the first one, this is the second. So regularity of R mod I is basically maximum of, so these are the J's and this is the I. So maximum of J minus I such that beta I comma J of R mod I is non-zero. So this is maximum of, so in the 0th position we have only 0. So it is 0. So in the first position uh, I is 1, J is 3 and 2. So 3 minus 1 and 2 minus 1. And in the second position it is just 5 minus 2. So it is basically 3. And this is the minimal free resolution which has length 2. Projective dimension of R mod I is basically 2. So without using this causal complex, one can directly compute the minimal resolution by the usual way, how we find the free resolution. That is also fine. But in that case, we need to find the kernels and do some computations. And that's all. So the second one. So here I is ideal generated by x times y. Now let's do it by hand because it's simple. So R mod I to 0 to R. So this is the natural surjection. Kernel is just x times y. Now we need some pre-module here. So let's take R and surjection and let's take the composition. So this is just multiplication by xy. But xy has degree 2. So we need to shift 2 degrees. And multiplication is injective because we are in an integral domain. So this is the minimal free resolution. So this is the minimal free resolution of R mod I. So let's calculate the regularity. So regularity of R mod I. So this is the 0th position, this is the first position. So this is maximum of 0 and we have only 2 minus 1. 2 minus 1. So this is 1. And projective dimension is also 1 because length is 1. And projective dimension of R mod I, this is also 1. Now the third one, which is complicated. So here I is x square xy yq. Okay. So for this ideal, we have already find the minimal resolution in the previous class. So how we have done it? So again, let's take R mod I. So let's subject it from R, take the natural map. So the kernel is I, which is basically x square xy yq. Then again inject it. Now we have 3 elements. So we need 3 R, direct sum R, direct sum R. Degree of this first one is 2. So we will shift it by 2. Degree of the second one is xy. Degree of xy is 2. Again minus 2. Yeah. So degree of the xy is minus 2. So this one is minus 2. Degree of yq is 3. So we need to shift it by 3. So we will just take surjection and take the composition. So this is x square xy yq. Now we need to find the kernel of this map. So if you go back to the previous lecture, then so I can directly write the free resolution from there. So you can go back to the previous lecture and check that it is just R minus 3, direct sum R minus 4, and the map is y minus x 0, 0, y square, and minus x. Or you can use the Macaulay 2 also to compute this. And this is injective. So this is the 0th position. This is the first one. This is the second one. Right. Now using this, we can find the regularity and projective dimension. So projective dimension is 2. That is clear. So projective dimension of R mod I is again 2. But what about regularity? So regularity is maximum of, here in the 0th part it is usually 0, but here first position 3 minus 1, 2 minus 1, 2 minus 1. So let's write it 3 minus 1, 2 minus 1, 2 minus 1. In the second position 4 minus 2, 3 minus 2. 4 minus 2, 3 minus 2. So clearly you can see that it is maximum. This maximum is 2. So regularity in this case is also 2. So in this way, we can find the regularity or projective dimension, but one can directly compute the regularity using Macaulay 2. There are commands. So you just have to enter the polynomial ring and the ideal and the command for the regularity or projective dimension, and you will get the answer. But if you want to do the computation by hand, then you can follow this way. Okay, so yeah, so I think we can conclude this session here. Yeah, so let's stop here. If you have any doubts, you can post in the discussion forum and we will try to answer that question or doubt.